In this video, we are going to only talk about one thing. We're going to talk about the invertible matrix theorem. And the invertible matrix theorem gives us a way to determine if a matrix is invertible or not. So the way the invertible matrix theorem is a little bit different than, the way this works is a little bit different than you are maybe used to. So with the invertible matrix theorem, we start out with let A be a matrix, and it's going to be a square matrix, so let A be an n by n matrix. Then the following are equivalent. And what we mean by this is either these are all true or they are all false. And so if you can show that one of them is true, then you will have shown that all of them are true. If you show that one of them is false, you will have shown that all of them are false. And so why this is called the invertible matrix theorem is one of these, the last one will be, the first one will be that the matrix is invertible. And so if you can show this for any of the other things to be true, you will have shown that the matrix is invertible. If you show any of the other things are false, you will have shown that the matrix is not invertible. So we start out with the first thing is A is invertible. So if you show A is invertible, you will show all the rest of these. But if you show A is not invertible, you will show that none of the rest of these are true. And it works the other way around as well. So the second thing is A is row equivalent to the n by n identity matrix. Meaning that you can follow a series of row operations that will get you all the way back to the identity matrix. Another way of thinking about this is that the reduced row echelon form of A is just the identity matrix. This is the same thing as saying that A has n pivot positions. What that's saying is that every column is a pivot column. There's a pivot position in every single column. The next is that the only solution to the matrix equation AX equals 0 is the trivial solution x is equal to 0. So the only solution is the trivial one, the all zeros solution. This happens when the columns of A form an independent set. This also occurs when the equation AX equal B has at least one solution for every B. So it has at least one solution for every vector B in Rn, meaning for every vector B that has n entries, so the right number of entries. Another way of saying this is that the columns of A span Rn. Meaning that you can get every vector in Rn by taking a linear combination of the columns of A. And you could say this is the same as saying there is a matrix, an n by n matrix C, such that C times A is equal to the identity matrix. This should be obvious that this is the same as saying that A is invertible, because C in this case would be A inverse. Similarly, if you can show that there is an n by n matrix D, such that A times D is equal to the inverse, or sorry, the identity, then D would be the inverse matrix of A, so A would be invertible. And finally, A transpose is invertible. What this says is that if you take and you transpose the matrix and you get something that you can easily show as invertible, then you showed that the original matrix was invertible. Or if you transpose it and you get something that you can easily show as not invertible, then the original was not invertible. There's a couple of key ideas in here that are very useful for us to think about separately. The first one is that the columns of A form an independent set, meaning that I can't take a linear combination of the columns of A and form the zero matrix, or thought of another way, I can't build one vector from the others. So what this means is if you see a multiple of one column as another column of the matrix, then you know that the matrix is not invertible. So for instance, if I look at a matrix like A equal, let's say -1, 2, 7, 3, 2, 4, 2, -4, -14, I know immediately that A is not invertible, because if I look at column 1 and column 3, I see that column 3 is -2 times column 1. So A is not invertible because the columns of A are linearly dependent, not linearly independent. So that's a quick way to tell. Another thing that will show up sometimes is if I have something along the lines of 1, 2, 3, 0, 0, 0, 4, 1, 7. As soon as there's a 0, 0, 0 in it, I can build that column by adding 0 times the first column. And so this is not linearly independent, so this is not invertible. And the fact that I can do this using the transpose of these matrices as well says that this works just as well if I use the rows, because the rows of A are the columns of A transpose. So I can use either the rows or columns and look for independent sets. Let's see, is there anything else that I really wanted to talk about? So yeah, the next thing that is worth mentioning is if you look at B and C, the being row equivalent to the n by n identity matrix, or having in pivot positions. Both of those are useful to know, but if you think about the process of figuring out what the pivot positions are, you're doing most of the work of finding the reduced row echelon form to find those pivot positions. So the process of finding those pivot positions or getting to the reduced row echelon form is similar amounts of work. And so frequently, if you're just trying to find there are in pivot positions, it's not much more work to go beyond that and actually find the invertible matrix. So sometimes you don't care what the invertible matrix is, you only care that it is invertible. But if you care, then eventually you're going to have to get that reduced row echelon form. You're going to have to do some kind of a process to find that inverse matrix. And so finding the reduced row echelon form is frequently the easiest way, is just try to find the invertible matrix and see, and if you can, then it is invertible, and you know all these other things as well. All right, that's where we are going to stop for today. This is very much a shorter video. I just wanted to cover a little bit of very basic information about how to tell if a matrix is invertible or not. And from here, we are going to be moving on from here, but I just wanted this to be in this week when you're taking the test, I wanted this to be a little bit shorter, and the homework this week is a little bit shorter as well. All right, I will talk to you guys later.